Okay, welcome back. This is section 3.6, roots and zeros. In this video, we are going to talk about how to identify the zeros of a polynomial function, how to use the zero product property to write a polynomial function, and how to use zeros and end behavior to graph a polynomial function. Okay, so first thing we need to make sure you understand is that the following statements are all equivalent. That means they mean the same thing, and if one of them is true, then all of them are true. First, x minus b is the linear factor of the polynomial p of x would mean that b is a zero of the polynomial function y equals p of x, which would mean b is a root or solution of the polynomial equation p of x equals 0, which means that b is an x-intercept of the graph of y equals p of x. Okay, so in example 1, let's go ahead and state the number and type of roots for this equation. So the first thing we want to do is find when this equation equals 0. And we, since it's a quadratic, have a bunch of different ways to do that. We can factor, do quadratic formula, or complete the square. And we learned from Module 2 that factoring is by far the fastest, so we check to see if that happens. And in fact, if we divide 6 by 2, we get 3, and 3 squared is 9. So we know that this is a perfect square binomial, or trinomial, excuse me, that can factor into x plus 3 quantity squared. And by the zero product property, we know that that means that x plus 3 times x plus 3 must equal 0, which means that either x plus 3 equals 0 or x plus 3 equals 0, because they're two factors. So to solve for x, if we subtract 3 on both sides, x equals negative 3 or x equals negative 3. This is what we call a double root, because it's the exact same number that happens twice, and you notice that the graph bounces off the x-axis. We'll talk about that later. So this has 1, so the number of roots is 1, and the type of root is that it's real, and there are 2 of them. So it's a double root, meaning negative 3 is happening twice, and so of course on a graph you can only graph that once. Okay, so pause the video. I want you to go ahead and try this. Your hint is there are 4 terms, so look at your factoring chart to see what the best strategy is. Okay, welcome back. Go ahead and take a look. Here are the answers. Cover it up if you don't want to see that. Okay, let's take a look at example number 2. In this example, again, we have it already set equal to 0, so we can use greatest common factor to take out an x. So we have x squared plus 25 equals 0. And since this does say the number and type of roots, that means we could include complex roots. So x squared plus 5, or 25, could equal 0, and x could also equal 0. So x equals 0, or x squared plus 25 could also equal 0. Well, x equals 0, that's a solution, so x equals 0. And then we have a sum of squares. So we use our difference of squares technique, so we can rewrite it as a difference of squares, right? Because if we're adding, we're really subtracting, and negative equals 0. So if this is a difference of squares, then we can think of negative 25 as 5i squared, right? So x squared minus 5i quantity squared equals 0. And so that means that x plus 5i equals 0, or x minus 5i equals 0. And so if we solve for x equals negative 5i, or x equals positive 5i. So in this case, we have 3 roots. 1 is real, and 2 are complex. So we have 1 real root and 2 complex roots. Okay, go ahead and try this on your own. Pause the video. Welcome back. Okay, I'm going to show you the answer, so cover it up if you don't want to see. And so before we start the next example, we need to understand complex conjugates. So if 3 plus 4i is a 0 of a function, then we know that 3 minus 4i must also be a 0. Because remember, we have the quadratic formula because you could do plus or minus because we're taking the square root of a variable that's been squared. That addition, right, means that if you have one complex root, you must also have its conjugate as a complex root. And conjugates are in the form of a plus bi and a minus bi. So a plus or minus bi is a pair of complex conjugates. So for example, if we know that 4 plus 6i is a root of this function, then we also know that 4 minus 6i is also a root because that's the conjugate. Okay, go ahead and try this example. If you don't want to see the solution, go ahead and cover that up. Okay, here's the answer. And so the other vocabulary word that we need to make sure you understand is integral. You'll see this come up in a couple problems. What integral means is in the form of an integer. And so if we say that a polynomial has integral coefficients, that means that the coefficients of the polynomials are all integers. So if we're writing an integer ax squared plus bx plus c, ax squared plus bx plus c, that means that a, b, and c, those numbers all have to be integers. Remember, integers are like -2, -1, 0, 1, 2, etc. Okay, so how are we going to do this? So what is a cubic polynomial function in standard form? Remember, standard form means that we have integer coefficients. So we have integer coefficients when our zeros are -2, 2, and 3. Okay, so if our zeros are -2, 2, and 3, then x equals -2. We know that x equals 2, and we know that x equals 3. And so if we solve each one of those for 0, then we know x plus 2, so we're going to add 2 to both sides here, x plus 2 equals 0. If we subtract 2 here, then x minus 2 equals 0. And if I subtract 3 here, then x minus 3 equals 0. And if those three factors all can equal 0, then if I multiply them together, they also equal 0. So this is kind of the zero product property backwards. So x plus 2 times x minus 2 times x minus 3 all equals 0. And since it says standard form, we know we need to distribute. So I'm going to go ahead and, so x squared minus 2x plus 2x minus 4. And I can't multiply in the x minus 3 yet because I want to simplify. So x squared, so this is 0, minus 4 times x minus 3 equals 0. And so now I can distribute here. So x squared times x is x to the third. X squared times -3 is -3x squared. -4 times x is minus 4x. And -4 times -3 is plus 12 equals 0. So here is our cubic polynomial in standard form that have zeros at -2, 2, and 3. Okay. Let's do one more example before I give you a you try. So in this case, it's a little bit different. In this case, we actually have 2 zeros at the same place. Remember, that's called a double root because it happens twice. So x equals -2, x equals -2, x equals 2, and x equals 3 would be our roots. And if that's true, then our factors, remember, we're going to solve for 0. So one factor would be x plus 2 equals 0. The next factor is x plus 2 equals 0. Solving this for 0, x minus 2 equals 0. And solving this one, x minus 3 equals 0. Okay, so when we look at this, we notice that we have x plus 2 listed twice. So if we're going to write this out as a set of factors, we could write this as y or f of x equals x plus 2 quantity squared times x minus 2 times x minus 3. And in math, we call this, so here's the equation written out, we call this a multiplicity of 2 because negative 2 is a root twice. So negative 2 has a multiplicity of 2 because it happens twice. And so from here, since again they wanted it in, remember, in standard form, so here is the polynomial in factored form. So this is factored form. But the directions want it in standard form, so let's go ahead and rewrite that in standard form. So we're going to do, this is x plus 2 squared, so it's x squared plus 4x plus 4, if I expand that. And then by distributive property, this would be x squared minus 3x minus 2x is minus 5x. Negative 2 times negative 3 is plus 6. Okay, and now I have two factors that need to be distributed. So x squared times x squared is x to the 4th. And then x squared times 5x is negative 5x squared. And then x squared times 6, or excuse me, negative 5x cubed. And then x squared times 6 is plus 6x squared. And then we have 4x times x squared, which is plus 4x cubed. And then we have 4x times negative 5x, which is minus 20x squared. And then we have 4x times 6x, which is 24x. And then next we have 4 times x squared, so plus 4x squared. And then 4 times negative 5x is negative 20x. And then 4 times 6 is plus 24. Okay, so we combine like terms. So we have 1x to the 4th. So g of x equals x to the 4th. And then we have negative 5x cubed plus 4x cubed is negative x cubed. And we don't have any other x cubed terms, so this is minus x cubed. And then 6x squared minus 20x squared is negative 14x squared. Negative 14x squared plus 4x squared is negative 10x squared. And then we have 24x minus 20x is plus 4x plus 24. And there is our polynomial in standard form. Okay, what if the root is not real? Well, we are going to do exactly what we did before. So in this case, if we have x equals negative 1, x equals negative 1, and x equals 5 minus I, so x equals negative 1, x equals negative 1, and x equals 5 minus I. Because this is a complex root, we also know that 5 plus I must also be a root, because you always have to have 2 complex or 4 complex roots or no complex roots. Right? Complex roots can't come in pairs or come in singles. They have to come in pairs. So here we have 5 plus I. Okay, so the first part is fairly straightforward. This, we're going to add 1 to both sides. So we have x plus 1 equals 0 is this root, and x plus 1 equals 0 is this root. So in our function, we're going to have x plus 1 squared is our first 2 sets. These are a little bit, take another step, but they're just as straightforward. So if we solve for 0, so same process, so x minus 5 plus I equals 0, and x minus 5 minus I equals 0. Okay, so here are our factors, right here. And so we can go ahead and just write that here. So x minus 5 plus I times x minus 5 minus I. And so this is all going to equal 0. And so just like we did before, we're going to go ahead and distribute these two products, factors. so that way we can simplify the I. So we're still going to keep the x plus 1 squared over here, but in this case, so we have x times x, which is x squared, and then x times negative 5 is negative 5x, x times negative I is negative ix, and then the next section, so we have negative 5 times x is negative 5x, and negative 5 times negative 5, remember this was a 5, is positive 25. And then negative 5 times negative I is positive 5i. And then the last one, so I times x is plus ix. And I times negative 5 is minus 5i. Minus 5i. And then I times negative I is negative I squared. Okay, so let's go ahead and simplify this. So I'm going to keep this factor over here so we don't forget about it. So I plus 2 or plus 1 squared. Okay, so we only have one x squared term, so x squared. And then minus 5x, that's negative 10x, and those are the only x terms. So negative 10x, and then we have ix plus ix, so that's 0. And then we have plus 25, so plus 25. And then 5i minus 5i, that again that's 0. And then negative I squared, well, negative I squared is, the negative I squared is negative 1. Okay, so negative minus a negative 1 is really plus 1. So this is plus 1, so this quantity here is going to be 26. So we have x plus 1 quantity squared times x squared minus 10x plus 26. Now this does not say that we have to write it in standard form, so we can just go ahead and leave this. So this equals a polynomial which we'll call g of x. You could call it f of x if you wanted to. And so there's your polynomial, because it does not say that we need to leave it in standard form, so we can just go ahead and leave it in factored form. If you wanted to expand this out to standard form, I wrote the standard form down here so that you can compare and practice your distributive property. Okay, I want you to go ahead and try. You can go ahead and put it through to standard form, because I think that's what I have up here, but you can also leave it as factored form also. Okay, welcome back. I'm going to put up the answer in a moment, so if you don't want to see it, go ahead and put your hand over. There you go. Go ahead and check your answers, and we'll move on to the next slide. Okay, so in general, multiple zeros are going to affect the behavior of the graph in a couple different ways. If there's only one of them, so if it's a single 0, then it's going to act like a linear function on the graph. If it's quadratic, that is, it's a double root. So you have x equals negative 3 2 times. It's going to bounce off the graph and act like a quadratic. If it's a cubic multiplicity, so as it happens 3 times, it's going to act like a cubic, and it's going to go so on and so forth. So for example, right here, you can say that that would be a double 0, but right here, that's a linear function, so that's probably only going to be a single 0 or a 0 of multiplicity 3, because it goes through the graph. So in this example, I want you to go ahead and try to sketch the graph using what we just did in the example. So take a minute, try that on your own. I'm going to show you the example as soon as you come back. Okay, welcome back. Here are the examples, so go ahead and cover up if you don't want to see it. And here's the next example. What I want you to do is take a look at this, and based on what you know about factoring techniques, which of these is not like the other one, and we'll talk about that in class. In the meantime, thank you so much for listening. If you want, go ahead and watch some more examples. Otherwise, complete the 3, 6, roots, and zeros reflection. Next up is Module 4. We're going to talk about operations on functions and composition. Thank you so much. Have a good day.